Hey everyone, today we're looking at simplifying Boolean expressions. Last lesson we looked at how to simplify Boolean expressions using Karnaugh Maps. This lesson we want to try to simplify how to do this with the many laws. So there are many rules to doing this. As we go through them today, I will try to give some practical tips for you to understand how to use them rather than try to memorize everything. It may make sense to try and seek patterns instead. So first, there are the general rules for both and or. Now, when we look at the names, there are a lot of names of these rules to remember. I think it's better to just focus on the principles and try to understand how they work. So first one is the identity rule, which I've highlighted partly in red. Since both inputs have to be true for a true output, if one is a 0, then the output will no doubt be a 0. So the annulment rule is kind of the opposite. And like I mentioned before, hopefully you'll start to recognize the patterns rather than the names. So in this case, since one input is already a 1, x determines the final output. So the output is whatever x will be. The idempotent rule for AND allows us to remove a redundant part of an equation by removing a variable. So in other words, x and x simply just becomes x. The complement rule simplifies our equation because the result of x and not x means that both inputs will always be opposite each other, and therefore the output can never be true. When we look closely at the result of general rules with an AND operator, we can see that the pattern is generally that the output will always either be false or x. Now let's look at these rules for the OR operator. So with the OR operator, we can see that the output is either going to be x or it's going to be true. So if we look at the identity rule, we can see that it's going to be x or 0. Or the annulment rule is always going to be true. The result of the idempotent rule is always going to be x. So the result of the complement rule this time is always going to be true. So we've looked at the general rules. Here are some more that also help us to simplify our equations. The first one is the commutative rule. The commutative rule is straightforward. The order of variables does not change the result for AND and OR. In other words, it doesn't matter which way the expression is laid out. Think of a distribution like regular math. AND is multiplication, OR is addition. You're simply distributing one operation across the other. If we put this into a table, you'll see that it's exactly the same. This is for the OR rule, and if we see the same for the AND, we can see that the result, when distributed, is exactly the same. Let's try to make a bit more sense of this, right? So in regular math, the distributive property, such as x and y or z, would be equal to x and y or x and z. And if we just show this here, we can see that this would be the equivalent of, like we said, the x is like an AND, so the AND is like an x, sorry. We'd be saying 2 times 3 and 2 times 4, and that's exactly what we're doing here. So when we simplify the expression, we're saying the new expression now expanded is 2 times 3 and then 2 times 4, and the result should be 14 in both cases. So the associative rule simply means it doesn't matter how you group the terms using parentheses. When you have the same logical operation repeated, the final result will be the same. In other words, another way to look at this is when you are ANDing or ORing 3 things together, you can do the operation in any order. So the absorption laws refer to one variable absorbing the other term. In plain language, that basically means that the absorption law shows how one variable can make the other redundant. So for example, x or x and y simply simplifies to x. This simplifies a complex expression by eliminating a redundant variable. Double negation shows that a double negative cancels itself out. So rather than saying the movie was not unwatchable, we could just say the movie was watchable. The two De Morgan's laws are an interesting one to look at. Essentially, they're both the same, but with different operators. In both, the overall negative bar is broken and then the operator is flipped. So not A or B is equal to not A and not B. And then the other way around, not A and B is equal to not A or not B. So in an exam, you might be given a question like this. You should recognize that A and not A is going to cancel itself out, and that this equation simplifies to just B. If we put this in a truth table, as you can see, the column for B and the final equation look exactly the same. Take a look at this second equation. Just pause the video for a moment if you want to, and try to work out what you think is going to happen next. So, similar to the last task, this time using the complement rule for OR, we should be able to see that A or not A is going to result in true no matter what. So this should simplify the equation just to B, since we can see that we've removed the part of the equation that's now redundant. It's always going to equal true. And so because it's an AND, we know then that this should just be simplified to B. This time, let's look at a slightly larger equation and try to break it down. We should be able to spot from this one, just like the last task, this equation also has the complement rule for OR. So for this reason, we should be able to take this section and we should be able to simplify it to 1, obviously. And because this is now redundant, we can now simply remove it from the equation. Why not pause this section of the equation and try to work out what would happen next? So now you've unpaused. Here we would apply De Morgan's law to the first segment of the equation, remembering that we break the negation bar, and then flip the operator. So this would be our result. Once again, pause here and try to think about, when we look at the rules we learned before, what would you do next? So now what we would do is we would apply the distributive rule over the whole equation, but in reverse. I've tried to simplify how this would look by removing the variables and symbolize everything with just x, y, z. And then in the last section, what I do again is remove the symbols and turn everything back to the variables that we were looking at before. Pause and go back to your notes if needed and look at how we worked out the distribution rule before. So guys, now that we're left with just this part of the equation, we should be able to see that the complement law for AND would mean that not B and B should simplify to just false or 0, which then leaves us with just this. And using the identity law, then we should be able to say that not A or 0 is just not A. Right, before we move on, why not take this last equation, the one that we just worked on, pause and try to produce that as a Karnaugh map, which is something that we did in our last lesson. To begin with, I'm placing the first one based on the first segment of not A and B. So here we can see that this would represent on our Karnaugh map of just two variables, that this would be not A and not B. This segment also has a not A, but also has or B. So in this case, we also need to fill in this part that has a 1 for B. The last segment also contains a not B or B, and these are already filled in. So that leaves us with just having to group our values. And when we look at our variables, we can see that B is changing from 0 to 1, and that just leaves us with a constant that is not A. And this is exactly what we had worked out earlier using the rules. Now, there's a reason why I'm showing you this. Obviously, I'd like you to be able to work out the equations using the rules that we've been through. But if you're stuck in an exam and it's a 3 to 4 marker, working out the equation on a separate piece of paper would earn you at least 1 mark using Karnaugh Maps. So let's go through one final example. Looking at this equation, again, it's a big long one and it might look complicated. So let's think about what we're going to do. To make it simple to begin with, before I ask you to work it out, let's remember that in precedence, the and bands together and tighter than the or, so we can separate our terms by ors, not inside the brackets. That means that we can do this to simplify things a little bit more. So we've grouped our items together. Just pause for a moment. Now you see what our equation looks like. What do you think happens next? So we should know that from the absorption rule that logically this can be reduced to just simply B. Again, pause, see what you think should happen next. Now, using the distribution rule, we should be able to see that this can be distributed over the and, like this. So, the result of a distribution rule, you can probably see, leaves us with duplicates. And that means that part of our equation is now redundant, so we can reduce this so it looks like this. So next, if we rearrange these terms, we can see that we can apply the absorption rule again. So let's rearrange it. And if we do that, that leaves us with our final simplified expression of B or A and C. So here's the whole equation. And once again, I'd like you to try and put this into a Karnaugh map. Pause it, try to work it out on pen and paper, and unpause it when you're ready for us to work it out together. Okay, so let's add our first two terms of A and B. And our second terms, we're kind of having to manually distribute here. When we add, I've color coded this, so you can see the first thing that we're adding is A and B in yellow. And then in blue, we're adding A and C. And then if we look at the last part of our equation, we're adding B and B, which I've colored in blue. And then we're adding B and C. So then with all parts of our equation done, we now just group our items together. And first in blue, we've grouped the biggest part of the equation that we can. So we have a grouping of 4. And the next group then would be a group of 2, making sure that we don't leave out the 1 on its own on the bottom right hand side of our table. So the next thing that we would do is then we would compare our variables in each grouping. And we could see that in the blue box, which is the first part of our equation, we can see that A changes from 0 to 1. And we can see that B stays constant, it's a 1 on both. And we can see that C is changing from 0 to 1 here. So that means that the first part of our equation is just B. And as always, we separate our groups with an or. So then let's look at the second part of our equation, which is, if we look at our variables, A remains constant at 1. So here we can see 1 and 1. And B is changing from 1 to 0. And C stays constant at 1. Which would mean that our equation, our simplified equation, just like before, is B or A and C. So guys, I hope that was useful. As always, I would recommend checking the link on our video, going to the website, checking the extra questions that we have for you on our worksheet, watch the videos again, take your notes, go over it again, especially with a topic like this, and try to cross-reference everything that we've talked about today with the notes that you're taking. So I'll see you in the next video, guys. Do your practice. See you in the next one.